So on to video number 2 about this redox stuff. Redox is all about oxidation numbers and swapping electrons. Some things are more selfish, some atoms, some elements are more selfish than others. So selfish elements, in my terminology, they're going to want the electrons more badly than someone who's less selfish. When copper wire reacts with silver nitrate, it forms silver metal. What is oxidized? Well, a chemist reads that and starts thinking in equation terms. Copper wire, that's going to mean copper solid, is a reactant, and silver nitrate react together. That means silver nitrate is a reactant to form silver metal. So silver metal is going to be a product, and that nitrate has to go somewhere, so copper nitrate is going to be one of your products as well. So if we go through and assign oxidation numbers among these things, metals are some of the most involved species in these redox reactions. Metals are some of the things that are most likely to be oxidized and reduced. So I'm going to walk through and assign my metal oxidation numbers. Copper is solid in an uncombined state. It's an oxidation number of 0. Copper in copper nitrate has a charge of +2, so his oxidation number is +2. Silver in silver nitrate has an oxidation number of +1 because his charge is +1, and silver in an uncombined solid state is a 0. So I can already detect that my silver changed oxidation numbers and my copper changed oxidation numbers. One of those things is going to be oxidized and one of those things is going to be reduced. If I also go through the trouble of assigning nitrogen in nitrate, I can think of as NO3 minus, oxygen's always -2, multiply it by 3, it's got to equal -1 when I add nitrogen into the mixture. So nitrogen is a +5 and oxygen's a -2. But it's a nitrate on the left side and a nitrate on the right side. So my nitrate oxidation numbers do not change. Nitrate is simply there to counteract the positive charge in silver and the positive charge in copper when those two react with each other. So if I go through and write half reactions, copper going to copper 2+, I'm going to put electrons on the products side. Copper going to copper 2+, 2 electrons on the product side. Silver going from a 1+, silver +1, to silver 0. Silver +1, +1 electron, put it on the reactant side, becomes a silver 0. Anytime the electrons are on the product side, that's an oxidation half reaction. Anytime the electrons are on the reactant side, that's a reduction half reaction. Because you cannot have oxidation without reduction, you can't add these electrons together, these equations. You can't add these equations together as is. You must balance them. And oh, I just realized my top equation is not balanced. This copper loses 2 electrons, so it means silver needs to gain 2 electrons also. So I multiply the whole equation by 2 in order to balance this thing out. 2Ag plus 2 electrons yields 2Ag. And I did put the 2 in the beginning here, but I totally neglected it and just realized it on my product side. Okay, so copper is oxidized because he lost electrons. Oil rig, Leoger, lost electrons. Silver is reduced because he gained electrons. 2 more terminologies that can be quite confusing. Copper is oxidized, therefore copper is the reducing agent. Agent means the thing that assists in reducing something else. Reducing agent assists in reducing something else. Therefore, silver, Ag+, is the oxidizing agent, the thing that assisted in oxidizing something else. The thing that is oxidized is always the reducing agent. The thing that is reduced is always the oxidizing agent. Whew. One more thing before we roll on to the next one. The copper here is a reactant. It is copper solid that is oxidized. The silver is a silver plus because the silver plus is a reactant. When you talk about something being oxidized and reduced, you're talking about on the reactants side of the equation. So we can't simply say silver is reduced because that would mean Ag0 is reduced. We're going to say silver ion or silver plus is the thing that is reduced. Okay. Oh, yeah, one more thing to clarify. The reducing agent always donates electrons. The oxidizing agent always accepts those electrons.
Displacement reactions are among the most common redox reactions. For example, a metal in a compound can be displaced by another metal in the uncombined state. When metallic zinc is added to a solution containing copper 2 sulfate, it displaces copper 2 plus ions from the solution. Zinc reduces copper 2 plus ions by donating 2 electrons to it, producing copper metal and zinc 2 plus ions in solution. Note that copper metal is depositing on the zinc bar. Also, during the reaction, the solution loses the blue color that characterizes the presence of hydrated copper 2 plus ions. Let's zoom in to view the reaction on a molecular level. Zinc atoms enter the solution as zinc 2 plus ions, losing 2 electrons. Zinc is oxidized. The electrons are gained by copper 2 plus ions, which are converted to copper metal. Copper 2 plus ions are reduced.
So in that equation between copper and zinc preferred to give up the electrons, while copper preferred to accept the electrons. Some things, some metals, some atoms, some elements are more selfish than others. So in that specific example, copper is more selfish than zinc. Copper accepts the electrons from zinc. That reaction never happens in reverse. All right, a little bit more.
Similarly, metallic copper displaces silver ions from a solution containing silver nitrate, AgNO3. Each copper atom reduces 2 silver plus ions by donating 2 electrons. Note the silver metal is depositing on the copper wire. Also, during the reaction, the solution turns blue due to the presence of hydrated copper 2 plus ions. Let's zoom in to view the reaction on a molecular level. Copper atoms enter the solution as copper 2 plus ions, losing 2 electrons. Copper is oxidized. The electrons are gained by silver plus ions, which are converted to silver metal. Silver plus ions are reduced.
So in that example, comparing copper and silver, silver is apparently more selfish. Silver would prefer to have the electrons over copper. So we're going to talk about a chart of selfishness, basically. So if we walk through that first example that was in that little clip, they showed zinc being oxidized and copper being reduced. Every time the thing is oxidized, that's called the reducing agent. The reducing agent assists in reducing the other thing. The reducing agent is responsible for giving up electrons, donating electrons. The oxidizing agent is responsible for accepting electrons. The terminology around this redox stuff can be quite confusing. Okay, so here's a couple of beakers kind of based on what that little clip shows. In this solution, it's zinc and copper, and zinc is the one that started out solid, but as the reaction progresses, the copper comes out of the solution. The copper ions that are dissolved in solution become solid copper within that solution. That's because copper is more selfish than zinc. When the reaction continues long enough, you got nothing but copper. All the zinc is totally dissolved into solution. That zinc metal dissolved as the copper gained its electrons. But when you put copper and silver together, copper is more selfish than zinc, but silver is more selfish than copper. So when you put copper silver together, silver ends up taking on all the electrons and making copper back into an ion in solution. So we're going to talk about a chart of selfishness. This is our chart of selfishness. The things up top are least selfish, ease of oxidation increases. Least selfish, most likely to give up electrons. The thing at the bottom is most selfish, most likely to accept electrons. So when you're given an equation like this first one and asked, will anything happen in this reaction? Identify your two metals on this selfishness chart Here's aluminum, here's copper. In this equation, for something to happen, aluminum has to give up electrons to copper. So because aluminum is higher on the list than copper, because aluminum, I should point out oxidation numbers, aluminum is a 0 right now, and copper is a 2+. We're always, in these equations, we're always aiming at ending with the ion that is charged in the beginning, so copper, becoming a 0 in the end, and the thing that's a 0 in the beginning becoming an ion in the end. Aluminum is always a 3+. That is not a balanced equation. I'm not trying to make it that way. I'm trying to point out what kind of equation we're looking for. So aluminum has to lose in this equation, and because aluminum is higher on the chart than copper, yes, aluminum will lose in this equation. That reaction will proceed in the forward direction. So the question is, will anything happen? Yeah. In order for zinc to go from zinc 0 to zinc 2+, and for lead to go from 2+ to 0, we need zinc to be above lead on our reactivity chart. Do you follow me? Zinc has to be willing to give up electrons, and lead willing to accept them. So find our two metals, zinc, lead. Zinc gives up, lead accepts. Yeah. Copper needs to be above lead in order for this reaction to happen. Here's copper, there's lead. No. Copper needs to be above lead for this reaction to happen. Ain't happening. Iron, whoops, apparently I did not draw stuff in for the last one. Iron needs to be, here's iron. Iron needs to be above nickel in order to be willing to give electrons to nickel. Iron above nickel? Yep. So the one other piece of information that's on this activity series, that's what this is called really, activity series, are these red arrows. This says displace hydrogen from acids. What that means is will react with acids in a certain way. So here's hydrogen, you see. These will react with acids in a certain way. These will displace hydrogen from steam, so that means water at high temperatures, that's steam. These will displace hydrogen from cold water. These are the most reactive metals that exist. If you got a little extra time on your hands, Google a YouTube video of someone chunking lithium into a lake somewhere. You will see hydrogen being displaced from cold water. So in this first equation, we're asking if silver can displace hydrogen from an acid. So really what we're saying is find the H on the chart, and silver needs to be above it, but it's not, so that one has no reaction. When you put silver in a reaction vessel with acid, this is acid, we got to talk about acids in the future, but that's a representative of acid. When you put silver in a reaction vessel with acid, nothing happens because silver is too selfless to react with acid. Okay, what about when you put sodium in with zinc? Well, sodium is way up here, so it's going to react with a ton of things, and zinc is below it, so yes, it will react. Sodium will become a cation. That means sodium plus, because sodium is not a stable 2+. And zinc will become a 0, a zinc solid. You got to balance the reaction, 2 sodiums. Now on a +2 charge on both sides, I've got the same number of elements on both sides. Completed equation, with one little exception. That is now aqueous sodium. So we started out as solid sodium. The sodium starts to dissolve in our water solution. All right, next. Lead and zinc. There's zinc again. And lead. This would mean that zinc must give up electrons to lead. Zinc is above lead. Is that possible? Absolutely. Zinc becomes its stable ion, which is a 2+, and dissolves in solution to become aqueous, while lead gains electrons to become a neutral, solid lead. The next one, copper needs to give up electrons to lead. Copper needs to give up electrons to lead. Copper is below lead. Copper is more selfish than lead. Copper ain't about to give up electrons to lead. Iron, in the bottom one, iron would need to give up electrons to lead. Iron needs to give up electrons to lead. Iron is less selfish because it's higher on the chart. Iron absolutely will give up electrons to lead. The thing that's a little bit tough about this one is the lead should become lead solid, but whether it should become iron 2+ or iron 3+ is a little bit ambiguous. I would need to tell you that because iron exists as stable 2+ and stable 3+. We'll make it a 2+ so that we can move on along and it's already balanced element-wise. So iron makes a stable 2+ and 3+. Yeah? That's the activity series. You're going to have to practice using quite a bit of that. Everything that we've talked about in these examples are all metals, or metals and metal cations. But in general, the cation is going to want to gain electrons. The metal is going to want to give up electrons. But the activity series says the transfer doesn't always happen depending on how selfish those different metals are. Cations take electrons, metals give electrons. Okay, I'm really done.